Hello everybody, we start and oops, I forget what is the number of today's lecture. 20. Maybe somebody knows what is number of section for today. 20 or 22, nobody knows. Okay. Last was 19. 20. 21. Uniform convergence. Sorry? 21 was uniform convergence, right? 20.1. Uniform convergence? Very strange. It should be even. Definitely it should be even. Something wrong. What is number of lecture? Номер лекции какой? 21. So it means last lecture section would be 19, not 20. It was mistake. So today is 20.1 and last lecture I made a mistake with numbering. So this is, in fact, that is continuation of that wrong 20.1. Koshi Criterion. Of uniform convergence of sequences. Definitely it should be a part of one section together with definition of the uniform convergence. So theorem 1, a sequence fn of x, and from 1 up to infinity converges uniformly on E if and only if for arbitrary epsilon greater than 0 there exists a number n natural such that for all n greater than n, for all p natural, and for all x in E, we have inequality f n plus p of x minus f n of x less than epsilon. Proof. Okay, let's start with necessity part, which is simply first necessity. So we suppose Fn converges uniformly on E. What it means by definition? By definition, it means that for arbitrary epsilon greater than 0, there exists a number n such that for all n greater than n and for all x in E, we have an equality fn of x minus f of x less than epsilon. That is uniform convergence of a functional sequence. Now, look, what is written here? We have inequality for arbitrary x and e. So what we do? Fix x and e. And this is valid for arbitrary little n greater than capital N. So in particular, it is valid for arbitrary natural p. We have for the same x, we have fn plus p of x minus f of x less than epsilon as well. And in fact, I can take epsilon over 2 for convenience. Why I can take here p, arbitrary p natural? Because if little n greater than capital N, then for sure n plus p is also greater than capital N, right? So I can consider n plus p instead of n here. That is what I do. Now, if we have those two inequalities, they imply together what they imply. By the triangle inequality, I can insert f of x so I inserted f of x with minus and plus, and then by the triangle inequality I write this. And both terms are less than epsilon over 2, so the sum is less than epsilon over 2 plus epsilon over 2, or less than epsilon, right? And then, okay, now forget about those fixing and so on, so let us analyze what we have as a chain of quantifiers. So for arbitrary epsilon, we found capital N such that for all n little n greater than capital N, and for all natural p, and for all x and e, we have an equality modulo fn plus p minus fn less than epsilon. So what is underlined is precisely the line which we wanted. So we obtained it, right? Okay, necessity is proved. Now for sufficiency. So now we have the chain of our quantifiers, let it be star. So star is satisfied. That is what we suppose. Again, fix x and e. Arbitrary, of course. So, look, so we fix this x, then what means star? Then star means that the sequence fn of x is fundamental, or is a Koshi sequence, right? Is a Koshi sequence. Is a Koshi sequence. So there is a sequence of numbers, x is fixed, right? So what is written? So for a while I forget about this. right? So what we have? For arbitrary epsilon, there exists capital N such that for all little n greater than capital, for all p natural, we have this inequality. That is precisely definition of Cauchy sequence. And we know from the first part of our course that if Fn is a Cauchy sequence, then Fn of x converges. So there exists a limit. Okay. I can denote it as I want, right? So let it be f of x. So there exists a limit. I denote it as f of x. Once again, I fix x and proceed just with a sequence of numbers. So for fixed x, we have a sequence of numbers. And the limit is denoted by f of x. Okay. Now, once again, forget about this fixing x in E, right? And go back to star. So, look at star once again. Now, I want to look more carefully at for arbitrary p in capital N, right? So we have for arbitrary p in capital N, we have this inequality, right? For arbitrary x, for arbitrary n. For a while, fix everything else. Only vary p. So p is arbitrary, right? Hence, I can push p to infinity, right? So p tends to infinity. Let p tends to infinity. So p tends to infinity. Everything else is fixed. N, x, all of them are fixed, right? But we know that if p tends to infinity, then what is about this limit as p tends to infinity? We know, so look, index tends to infinity, right? Then we have a subsequence, or better to say shifted sequence, right? Indices are shifted of that sequence, and the limit is f of x, right? So the limit here is f of x. And we know that we can take limits in inequalities. Inequalities, they are preserved up to non-strict, right? So if we have a strict inequality, then after taking limit, strict inequality may be transformed into non-strict, right? We cannot guarantee that strict inequality will be preserved. That's impossible. So, what we obtain, let me rewrite once again. Epsilon was arbitrary, right? Capital N was chosen before. All other, little n and x in E were taken again arbitrarily. And so star after taking limit is transformed into f of x minus fn of x less or equal than epsilon. But look at this line. That is precisely up to this inequality, right? But of course, since epsilon is arbitrary, small, it doesn't matter if we have strict or non-strict inequality here. So, or if you want, you can start with epsilon over 2 here. Then less or equal epsilon over 2 less than epsilon. So, in any case, what we have is precisely by definition, it means that fn of x converges to f of x uniformly on E. So we have proved our theorem. So you see, comparing with standard Koshi Criterion, so okay, it was like a sequence is a Cauchy sequence if and only if it converges. I mean, if we collect all assertions about Cauchy sequences from the first part of our course. And so Cauchy sequence means that we have everything without that, right? And you see, so like for definition, to get definition of uniform convergence, we need to insert quantifier for arbitrary x after the existence quantifier, right? It gives us uniform convergence. So Koshi Criterion is the same story with Koshi Criterion. To obtain Koshi Criterion of uniform convergence, what do you need? You need to take standard Koshi Criterion and insert quantifier for arbitrary x after existence quantifier. So first the existence, then for arbitrary x. Right? So if you take this for arbitrary x outside, then that is Cauchy criterion for usual convergence. If you change position of the quantifier for arbitrary x, you obtain Cauchy criterion for uniform convergence. Okay? Okay. So, now the main topics for today. So in fact, that was, yeah, I would say 20.1, section 20.1 should be one section about uniform convergence of sequences. Definition plus Cauchy criterion, but unfortunately I was not able to finish it last time. So 20.2 20.2 uniform convergence of functional series. I'll start with definition. A series sum n from 1 up to infinity fn of x converges uniformly on E if the sequence of partial sums as n of x equals to sum k from 1 up to n f k of x converges uniformly on E. So, uniform convergence of series is nothing else but uniform convergence of a sequence. So, in quantos with quantifiers, that is, for arbitrary epsilon greater than 0, there exists capital N natural such that for all n greater than this capital N, for all x and E, and we have convergence of Sn, so that is Sn of x minus S of x less than epsilon, or I can rewrite it in more details, so that last equation, inequality, like sum fk of x minus S of x less than epsilon, or if we denote, so what is S of x? S of x is just the sum of our series, and we can rewrite the last inequality like sum k starts from n plus 1 up to infinity fk of x less than epsilon. That is inequality for remainder. Okay, that is just a definition. And of course you can ask why we need to consider uniform convergence of functional series separately, because nothing new comparing with former definition of convergence of partial sums. And in fact, we can formulate, for example, theorem 1, Koshi Criterion. Of uniform convergence of a series. So, the series sum fn of x converges uniformly on E if and only if for arbitrary epsilon greater than 0 there exists capital N natural such that for all little n greater than capital N, for all p natural, and for all x and E, we have an equality sum k from n plus 1 up to n plus p f k of x less than epsilon. Okay, we don't need to prove it. Why? Because all what is necessary to write it as a proposition, you should combine definition of uniform convergence of a series. So uniform convergence of a series is equivalent to uniform convergence of the sequence of partial sums, right? Sn. Now, what is about uniform convergence of the sequence of partial sums? We have Koshi Criterion, and for Koshi Criterion, you should consider this. In Koshi Criterion for uniform convergence of a sequence, right? But look, what is it? Sn plus p of x minus Sn of x. That is precisely what is written here. Because you take the sum of the first n plus p terms and subtract the sum of the first n terms. So first n terms are cancelled, and what remains is precisely that one. And very important corollary. And that is also term test for uniform convergence. So if the series converges uniformly on E, then Fn converges to 0 as n tends to infinity uniformly on E. So if we have uniformly convergent series, then general term Fn converges uniformly to 0. That is an analog of necessary condition for usual series, or term test for usual series, right? So if a series converges, then general term tends to 0. And how to prove it? Look, what is written here? Arbitrary p natural, right? So take p equals to 1. What remains? Some k starts from n plus 1, finishes at n plus 1. It means just one term we have, right? One term f n plus 1. So no sum, and that is precisely, now forget about p, right? That is precisely the definition that fn plus 1 tends to 0, uniform. That is the proof. But be careful. Let me compare. So, compare functional series and sequences. So, there was a corollary about how to prove that Fn doesn't converge to F uniformly on E. There was a consequence. So there exists a sequence xn in E such that Fn of xn doesn't tend to okay, for example, I should insert here xn tends to x naught, doesn't tends to f of x naught, and goes to infinity. So Or maybe, okay, maybe I'll change it a little bit. Let me write like that. Fn of f of x n doesn't tend to 0. That is more useful. That is more useful. That is very popular condition to prove the absence of uniform convergence of a sequence. So if you want to prove that a functional sequence doesn't converge, then you find a sequence of points such that the difference between Fn and f doesn't tend to 0 at those points. That is sufficient to prove the absence of uniform convergence of a sequence. But for series, that is not true. So, look. Doesn't converge uniformly on E. Popular mistake. Oh, that is not true. There exists a sequence such that doesn't converge. So you see, popular method to prove that a functional sequence doesn't converge uniformly. You find a sequence, right, such that this Fn of xn has no limit, for example, right? But if you find a sequence xn such that this series doesn't converge, it doesn't say anything. Why? Because, look, what is uniform convergence of a series? Uniform convergence of a series is equivalent by definition to uniform convergence of partial sums, right? So it means if we want to prove that the series doesn't converge, we have to look at the sequence of partial sums, Sn, right? And it means if we want to use this criterion, we should take the same xn for one partial sum. And it means we have to take one value xn for every f1, f2, and so on up to fn. You understand? And here we have absolutely different thing. So, if you want to use this criterion, so here, imagine you have partial sums, right? But if you have here partial sums, that is completely different from partial sums of that series. These are absolutely different things. That is why it doesn't work. Okay. So, now more practical tests to prove uniform convergence of a series. Very popular. very popular. So theorem 2, Weierstrass test. So if for arbitrary x in E and for arbitrary natural n, we have the following inequality: fn of x less or equal than cn, and the series converges, then the functional series fn of x converges uniformly on E. Proof. We'll use Koshi sequence. So the series of numbers converges Koshi Criterion for series. So by Koshi Criterion for series, what we deduce: for arbitrary epsilon greater than 0, there exists natural n such that for all n greater than this capital N and for all p natural, we have inequality Ck less than epsilon. So that is Koshi criterion for series. Koshi criterion for series. Now look, I take all those quantifiers. So let them be the same. And then for arbitrary x in E, I can write the following estimate. Sum k from n plus 1 up to n plus p fk of x. So first of all, triangle inequality. Triangle inequality says that we have sum of modulus of fk. Next, I'll use the condition fk of x less or equal than ck. So I replace and of course we observe that all Cn should be non-negative, right? Otherwise this inequality is impossible. And it means that I can put here modulus. All of them are non-negative. And that is less than epsilon, right? So what is underlined says by Koshi criterion for uniform convergence of series, right? That we have uniform convergence of our series. the proof is completed. Okay, let's have a break. So, Weierstrass test is very simple, but nevertheless very powerful tool. But sometimes it is not sufficient. So we need to find other tools for uniform convergence, like for usual convergence of series. And you see, once again, Dirichlet test appears. Here 3. Dirichlet test. But of course, here I should insert what is about, because we know two Dirichlet tests at the moment, right? One for improper integrals, another for series, usual series, now for Dirichlet test for uniform convergence. Of series. To formulate it, let me recall. So, recall Dirichlet test of convergence of series. So, we had two suppositions. The first one, sums, partial sums are bounded. The second one, Bn monotone and convergent to 0, right? Then the series A and Bn converges. So now look how to formulate. So we had Dirichlet test for convergence, right? Now we want to formulate Dirichlet test for uniform convergence. And in fact, very simple rule how to formulate it. You should insert word uniformly everywhere. So, look here. In words, what is it? Partial sums are bounded, right? And here, monotone and convergent to 0. So where we can insert words uniform? Of course, here. And then we need what is uniformly bounded. So we know what is a sequence is bounded, right? So let me formulate before to finish the theorem. So definition. A sequence is uniformly bounded on E if there exists a constant C, real constant, such that for all natural n and for all x and E we have fn of x less or equal than C. So look, what is uniform boundedness? Look here, without uniform, what it means bounded? there exists a constant such that for all n you have inequality. So if you change the position of this quantifier for arbitrary x, if you put it before, what it means? It means that the sequence of n of x is bound for arbitrary x, right? And it means that constant, in fact, depends on x, right? So if you change the position of this quantifier, insert it at the first place, then c depends on x, and what you have boundedness of fn of x for arbitrary x. For arbitrary x, fn of x is bounded, right? But now, what means uniformly bounded? Uniformly bounded means that you have one constant in advance for all x simultaneously. So you can choose a constant such that fn of x less or equal than this constant for all n and for all x. So uniform means that the constant does not depend on x. Like it was for definition of uniform convergence. There exists capital N, does not depend on x, only on epsilon. Okay, so return to our theorem. So suppose, first, the sequence of partial sums, okay, let it be again k from 1 up to n ak of x, and from 1 up to infinity is uniformly bounded on E. And second, the sequence Bn of x is monotone for all x in E and uniformly convergent to 0 on E as n tends to infinity. Then the series an of x, bn of x converges uniformly on E. So you insert uniform everywhere where you can. And it gives you a test for uniform convergence of a series. So proof. For the proof, we'll use Koshi Criterion, right? So what we want to use Koshi Criterion, and it means that we want to check the following sequence of quantifiers. That is what we want to prove according to Koshi Criterion for uniform convergence. We need to estimate somehow such a kind of sum from n plus 1 up to n plus p. Okay, how we will do it? For that reason, let me introduce the notation. So let's say b, capital B, k of x, let it be by definition I have, sorry, ak, capital AK. Capital AK of x, let it be sum for j starts from n plus 1 up to, let it be k, aj of x. So, let me write what means uniform boundedness. Uniform boundedness means there exists a constant c such that for all n natural and for all x in E we have an equality sum k from 1 up to n ak of x less or equal than c. And what we can deduce from that inequality about capital AK? What is capital AK? We can represent it as a difference between sum j starts from 1 up to k minus the sum j starts from 1 up to n j, right? So just cancel those, the sum of the first n terms. And each of those partial sums is bounded by capital C in modulus, right? Hence, by the triangle inequality, we deduce that modulo ak of x less or equal than c. Once again, for arbitrary x and for arbitrary k, right? Of course, k here should be k greater than n, otherwise it makes no sense to consider that expression. Okay, so we have, oh sorry, not c, 2c, right? 2c we have, because every term here is less or equal than c in modulus, and triangle inequality transforms difference into the sum, right, when we put modulus. Okay, now recall I want to estimate such a sum. So we proceed with that, n plus 1 here, a k of x, b k of x. So I represent little a as a difference between capital AK and capital AK minus 1. Why? Because capital A is the sum of all terms aj starting from n plus 1, right? Of course, here, yeah, I supposed for k greater than n, right? But if k equals to n plus 1, then a n appears. So a n of x, let it be just 0. Because what means a n? We have starts from n plus 1, finishes at n. Wrong, right? It means we don't sum up anything. We have 0. By definition. Okay, then I can write every little ak as a difference between capital A, k and capital A, k minus 1. Now once again we apply Abel transform. Abel transform, which we applied several times in fact. So how we do it? The very last term, namely a n plus p of x, has only one little b. The smallest index gives us 0, right? So I don't subtract the smallest. And all other terms, okay, what I have, plus sum k from n plus 1 up to n plus p minus 1. For ak of x, what I have? I have bk minus bk plus 1. You see, every capital A has either b with the same number, right? Or b with number which is greater than number here in 1, right? 1 plus this index, but with coefficient minus 1. That is what is written, right? Now remember, I want to estimate, right? So I put modulus, and then apply triangle inequality. So we apply triangle inequality, a n plus p of x times b n plus p of x plus the sum k from n plus 1 up to n plus p minus 1 modulo ak of x times modulo bk of x minus bk plus 1 of x. Now look what I want to use. First of all, I'll use this estimation for all capital AK, right? Each of them is less or equal than 2c. So less or equal than, let me put it here, so 2c times bn plus p of x plus the sum k from n plus 1, okay, I'll put 2c outside of them, sum bk of x minus bk plus 1 of x, right? So I estimated every capital A by 2c, right? But now look what we have in this sum. Remember what we suppose about our sequence B. The sequence Bn is monotone for arbitrary x. And if it is monotone, so look, choose fix arbitrary x, right? We have monotone sequence here, right? And it means signs of every term are the same, right? So each difference, so for fixed x, all of them are either positive or negative, right? All of them. Because the sequence bk of x is monotone, right? Now look, if we sum up modulus of numbers with the same signs, for example, if you sum up all negative numbers, modulus of negative numbers, then this is the same as to put modulus outside, right? Because if signs are the same, right, then sum of modulus equals to modulo of sum. So here we heavily use monotonicity. And in fact, we see it doesn't matter in which sense. So plus 2c times modulus. That is because of monotonicity. But then what we have, on the modulus telescoping sum, right? All terms cancel each other, and what remains, once again, equals to bn plus p of x plus 2c times modulus of what? Okay, the smallest bn plus 1 of x minus bn plus p plus 1, right? But wait a minute. I'm sorry. N plus p minus 1 here should be. Minus 1, so n plus p. Because here it was minus 1. I forget this minus 1. Okay, now the last condition which we didn't use, and now it's a time to use it. Which condition? Uniformly convergent to 0. What means uniformly convergent to 0? Bn uniformly convergent to 0. So Bn is uniformly convergent to 0. I'll write shortly like that. Bn uniformly convergent to 0, by definition, what it means? For arbitrary epsilon greater than 0, there exists capital N natural, such that for all n greater than this capital N, we have modulo Bn of x is less than epsilon, right? But to make it better, what I should use here, I have 6, right? Epsilon over 6c. Why? Because now, look, so I take arbitrary epsilon greater than 0. We choose capital N, such that for all n greater than capital N, and also for all p natural, what I have? Bn plus p, number is greater than n. So Bn plus p less than this epsilon over 6c, right? Here modulus of difference less or equal sum of modulus, right? Once again, every index here is greater than capital N. So all of them, all of those b, are less than epsilon over 6c, right? And altogether what we have? We have 3 equal terms. Each of them equals to epsilon over 3, so epsilon. And that is valid for all x. Oh, the most important thing I forget. For all x in E, of course, right? Uniform convergence. Uniform convergence. And here for all x in E also So, okay, I started from this one and finished here. So, what is underlined is precisely what we wanted to prove from the beginning. So, the theorem is completed. Okay, analogously, we can prove Abel's test for uniform convergence of series, and analogously to usual series, we change restrictness. So now we suppose that the series, let's say n of x, is uniformly convergent, uniformly converges on E, and the sequence is monotone and uniformly bounded. Bounded on E. So, what we have is that one now. I don't want to erase the proof because I will repeat it practically. So, once again, the theorem is as follows. Abel's test for uniform convergence of series. Suppose, firstly, the series n of x uniformly converges on E, and the sequence Bn of x is monotone for arbitrary x and uniformly bounded on E. Then the series converges uniformly on E. Then the series converges uniformly on E. And proof, we use the same scheme. So we estimate the same difference, and practically every line here is not changed. The second half of the blackboard, even I don't need to change. It's absolutely the same. But over there, it's completely different. Why? So look. So I estimate this. Once again, I proceed using the same notation for capital AK. I don't need now this representation. It is not important for me anymore. So I write it like that. I apply Abel's transform. So here everything is the same. But then what we do, so look, what we did for Dirichlet test. Capital A was bounded by a constant, right? But little b were very small because b tends to 0, right? Now we change roles. So look, every term here, one is small, other is bounded, right? Now we change the roles. Here we had bounded capital A, small b, small little b, right? Now small will be capital A and little b will be bounded, right? Because look, what we suppose now? We suppose Bn is uniformly bounded, right? So Bn is uniformly bounded, hence we have Bn of x less or equal than, okay, let me change to capital M to not mix with former proof, right? Capital M, right? So, and then, look, what else I should do? I should apply uniformly convergence of our series, right? So, because of uniform convergence of our series, I use Koshi Criterion, which says that for arbitrary epsilon, there exists capital N, such that for all n greater than capital N, and for all natural P, and for all x in E, I have the following estimate. That is precisely, okay, once again, I replace it by epsilon over 6m now. M is chosen before, right? Why I choose like that? Because what is it? That is precisely capital A with number n plus p of x, right? And p is arbitrary here, right? Now go back. N plus p less than epsilon over 6m. Here also every term is bounded by epsilon over 6m. So I can estimate this sum like that. So every capital N, A, is estimated by this. Right? So, like before, I estimate each of capital A, but not by a constant, but by a small number now, right? So, before, we could estimate capital A only by a constant, right? Because we supposed only boundedness, uniform boundedness of partial sums, nothing else. Now we suppose uniform convergence of this series, and it guarantees that all capital A with sufficiently large numbers are small, very small. And that is what we use here. Capital A are small, but little b are bounded. But before, what we need, what's important here, look, we have arbitrarily many terms, right, for this sum. But remember, B is, the sequence B is monotone, right? It means once again, we can put modulus outside, right? Because every term here has the same sign, right? And it means we can put modulus outside after that telescoping sum, right? So I can rewrite it as epsilon over 6m times bn plus p of x plus epsilon over 6m times b n plus 1 of x minus b n plus p of x, right? And after that, as we know, the sequence Bn is uniformly bounded, so every term here is bounded by capital M, and altogether, oh, 6m is too much. So I have less than epsilon over 2. Okay, that is less than epsilon. So too much. It was sufficient to divide by 3, right? Not by 6. But it doesn't matter. So, once again, we have proved our result by applying Koshi Criterion. Okay, these are main tests for uniform convergence, and of course now it's a good point to consider an example. And I have only 4 minutes. It's pity. Okay, I'll start this example. So example. Example. Such a series sine nx over n power alpha. So, first, study uniform convergence, where we have uniform convergence. Look, if we estimate like that, very rough estimate. So we know that sine is bounded by 1 in modulus, right? So we can estimate like that. And we know this series converges, in fact, if and only if alpha is greater than 1. And let me emphasize. Look, so for alpha greater than 1, we can use Weierstrass test. It works very well here, because you see, Cn, that is Cn, right, which converges, right, for alpha greater than 1. And by Weierstrass test, so by Weierstrass test, our series converges uniformly on R, on the whole real line, for alpha greater than 1. But be careful. Look, here it's equivalent, right? But I didn't write converges uniformly on R for alpha greater than 1 only. Why? Because how Weierstrass test works. If the series converges, and we estimate it like that, right? Then the series converges uniformly. But it doesn't say that if this series diverges, then the series does not converge uniformly. No. You see, Weierstrass test works only in one direction, if you want to prove that a series converges uniformly. It doesn't say that there is no uniform convergence. So if this condition is not satisfied, this series diverges, but it says nothing about the uniform convergence of our series. Okay, only first easy part, and we'll continue tomorrow, I hope. That's all for today.